So, good morning. It's Professor Katz answering your questions on this very snowy day. I can't get anywhere anyway, so I might as well sit here and answer some of your questions. Before I start, I want to say what questions I'm not going to answer and why. I'm not going to answer questions about how do you do specific calculations or the details of calculating the standard deviation. There's a couple reasons. Number one, in your reading, I really want you to focus on the concepts. I want you to skim over that part. I don't care if you don't really understand it, because that's not the purpose of what we're doing. What we're doing is to understand statistics, not to do lots of things by hand. And that's the second thing. When you do these calculations on a test, they're always going to be done on your calculator, unless for some reason you just love to do calculations by hand, in which case, I can't really help you. Maybe see a doctor or, I don't know, become a math professor. Addiction to calculations can ruin your life. Let me warn you. It can turn you into a math professor. So just take that into consideration. So that said, my answers are going to focus on what the things you asked about mean, not just how to do them. And the other thing is, you'll be doing them in class. Yes, on a calculator, but you will get some experience doing them. That's what's going on in the class. And it does bring you to the next step. First, you need to have the basic understanding, which is what my answers today are designed to give you. Then there's the calculations you're going to do in class and ask questions if you need to, and the presentation on that. And then I can bring you to the next step once we've done those through the mini lectures in class. Okay, that said, I've gotten a fair number of questions about the standard deviation. And there's not a lot I can say about the standard deviation. Keep the following things in mind. Your textbook gives you a formula, and that formula doesn't care what type of data you've got. Okay, and I don't just mean the fact that we don't care if you're looking at a sample or a whole population or whatever, because right now we're just describing the data. What I mean is it doesn't care how your data is distributed. So to review, I'm just going to draw over here and then I'll show you. We have unimodal symmetric. We can have unimodal skewed. I've made this left skewed. I can have a bimodal symmetric. And of course I can have bimodal skewed. Just make one hump of the camel bigger than the other. The autofocus is giving me a little trouble here. Hopefully you saw that at some point. Now, the standard deviation makes a lot of sense when we're talking about symmetric unimodal data. The reason is, when data is symmetric, you should have read this in your text, regardless of unimodal or not, the mean and median will be equal. So there's really only one good concept of center. When it's bimodal, that concept of center is maybe not the most useful. Maybe you should break it up into two groups. But for what we're doing right now, there still is an identifiable center. And it's the same whether you're talking about a mean or a median. Okay, not the same if you're talking about a mode, obviously. Whereas when it's unimodal, everything coincides. The standard deviation is about how far you have to go from the mean to get certain quantities of data. So if I have 100 people that I've measured their heights from, I'm going to use this example through the rest of this video answer. I've measured the heights of 100 people. I find the average, the mean, of their heights. The question now is, okay, well that's the average, but how many live at or near the average? And how far do you have to go to see more data? So maybe we're talking about something that's unimodal symmetric. It could look like this. or it could look like this. And what I'm showing you there is it can be tall and skinny or short and fat. If it's tall and skinny, it means they're clumped around the middle, the mean. If it's short and fat, they're spread out widely. The standard deviation is going to give me a measure of that, quantitatively. Okay, your textbook shows you the formula, and it's kind of what you'd expect. How far is each point from the average? And then you take those and combine them in a certain way. What you actually do is you get the variance and then take the square root of variance. And that's just done so that variance will always be positive. And it was really done so that we can take each one, take its difference from the mean, and square it. The reason we like to square things is so that we always get a positive number. So one thing being really far, another thing being really far, doesn't just cancel out. They're both positive when you square them. So it increases how far things spread, which is the way it should be. In any case, it's a numerical measure that tells me how far I need to go to get clumps of data. We'll see in the future that we can also use it to kind of standardize our data, which is why it's called the standard deviation. The next chapter, in fact, is called the standard deviation as a ruler. And that's exactly why it's called that, because we're going to be using the standard deviation to carry out this technique of comparing different data sets. But for now, what it is it's a measure of how far you need to go. Now, I gave you the 68, 95, 99.7 rule, and I'm still going to say that's for specific instances. It doesn't always work. It works for one very common and very useful distribution, which we'll be talking about in the weeks to come. But just for now, know the larger the standard deviation, the further you have to travel, the further you have to be willing to go from the mean in order to get a large portion of your data. And the extreme of that is a symmetric bimodal distribution. If you look at a bimodal distribution, in the middle you've got a low point at the mean. There's very few data points at the mean. You've got to get all the way out to the two humps to get a significant portion of the data. You're going to have a very high standard deviation. Obviously, if it's unimodal, symmetric, very tall and skinny, you're going to get a relatively low standard deviation. The same concept of how far do you need to go from the center to get certain portions of data is also applied to the median. And doing that is particularly useful, as we discussed last week, with skewed data. Because the mean is not resilient to skewed data. It's really moved a lot. In fact, as we'll look at in class, when I have data that's skewed, let's say, to the left, the mean and median are both to the left of the mode. But the mean generally is further. That's a general rule. The mean gets pulled harder because the mean responds to the actual numbers, the median responds to how many numbers there are. There are some exceptions, but that's the general rule that we'll work with. Okay, so as we now, can I take the skewed data and apply a standard deviation? Yeah, I can always calculate a standard deviation. It just doesn't necessarily mean very much. It's not particularly informative if my data is not symmetric. It's somewhat informative if it's bimodal, but not quite as informative as it would have been on the unimodal symmetric. We can still use it as long as it's symmetric. Now, when we turn to the 5-number distribution, again, I can use it for anything, but I tend to use mean standard deviation for symmetric data, especially when it's unimodal, and the 5-number summary when I'm talking about data that's skewed. When I look at a bimodal skewed data, I tend to give both, because that's complicated data. I need to get as many descriptors as I can get. So the 5-number summary relies on the idea of percentile, which a few of you asked about. A percentile is just give me a value that a certain percent is below. So going back to the example of heights, I've measured the heights of 100 people. I choose a height, maybe it's 6 foot, such that 75% of the population that I measured, that is the people I've measured, whether it's a sample or a population, doesn't matter, is shorter than that height, exactly 75%. That's called the 75th percentile. The 25th percentile, similarly, is somebody who 25% or shorter than. Maybe that's 5'2". Now, the median is just the 50th percentile, if you think about it. Just two ways of saying the same thing. The mean has no relationship to percentiles. You can't say where the mean will be on the percentile graph. It varies in different samples or different groups you're studying. So what the 5-number summary consists of is the minimum, the shortest person you've looked at, the maximum, the tallest person you've looked at, the median, 25th percentile, and 75th percentile. The distance between the 25th percentile and the 75th percentile, not the actual numbers, just the distance between them, is called the IQR, the interquartile range. Now, the larger that IQR is, again, the further I need to go from the center to get a significant amount of data. If the IQR is very small around the median, it means half of the data is clumped in right around the median. If it's very spread out, it means that's not the case. It's more spread out. So the IQR is kind of the corollary in this type of data of the standard deviation. Now, 5-number summaries are nice if you can make sense of them. You look at them, you try to understand what's going on. But it's been found a lot of people really struggle to look at 5 numbers and understand what's happening. As a result, statisticians came up with a visual way of describing it. And it's a very nice big thing because most people are able to just glance at this visual representation. It's called a box plot, and say, oh, okay, now I understand what your data is like. So the box plot consists of draw a number line. You can also draw it just on a graph parallel to one of the axes, either horizontal or vertical, whichever you think looks better for the purpose of what you're displaying. And then you just measure it against one axis. Just keep in mind it's one-dimensional, not two. Mark off the median with a little line, the 25th percentile with a similar line, the 75th percentile with a similar line, and draw a box using the two outer lines, the 25th and 75th percentiles, and the median line will be inside, and then just draw lines outside reaching all the way down to the minimum, all the way up to the maximum, and you get a picture like this, one on the bottom. Now remember, when I say the 75th percentile, I'm not talking about a percentage, I'm talking about a height. So the variable that this is stretching across, whatever number line I'm on, is heights. So the far left point is the shortest height encountered. The far right point is the highest height encountered, and so on. And looking at these things right away, you can get a pretty decent understanding if you know what you're looking for. So first look for where the box is in the plot. So if I happen to have the box shoved all the way to one side, what does that mean? It means 50% of the data is inside the box. Half of the people I've studied, maybe I've studied 100 people, so 50 of them have heights inside that box. Of the rest, the other 50% is distributed over the outer line portions. So 25% of the data is in that little tiny piece to the left, and 25% of the data is in that big piece to the right. So what does that tell me? Oh yes, you can't answer because it's a video. It tells me there's a skew amongst the outer 50%. There's a lot more clumping of the data, a lot higher frequency of data to the left than to the right, making this right skewed. When you go to the right, it reaches further but with less frequency. When you go to the left, values have higher frequency. As a result, doesn't reach as far. So that's the case. And then within the box, I have to look at where is the median within that box. And I apply basically the same type of reasoning. Sorry, I'm on duty because of the blizzard. I've picked up extra duty time, and so I have the radio open. I'll wait till that passes. Okay. And similarly, if the line inside the box is shoved all the way to the left of the box, that means that the data is really clumped in. The 25% are in a very narrow portion to the left of the median, and the other 25% is more spread out to the right of the median. And you can imagine the different combinations. I can have the box shoved to the left and the median shoved to the left. I can have the box shoved to the left, but the median shoved to the right within the box. Okay, and just for your own edification, try to take those and think about them and say, well, what's going on here? What would a frequency distribution look like in terms of the graphs that we've drawn where we have the heights on the x-axis and how often they occur on the y-axis? What would that look like for the type of data that I just described, where the box is shoved all the way to the left, but the line inside is all the way to the right? So one's telling me it's skewed left, one's telling me it's skewed right. Think about what it looks like and how much information we just conveyed on a very quick glance at a picture. Okay. Another challenge problem for you to think about. Is it possible for the median to equal the 25th percentile? And how can that be? Okay. So we've talked about box plots, we talked about standard deviation. We've emphasized that I want you to have an understanding. I want you to be able to look at a report on data and understand what it means. And that the calculations are going to be primarily done by a calculator. And understand that's not just to make your class easier. It's to push you in the understanding direction. Okay, because when you sit down to take a test, if I made you do the calculations by hand, it would take you more time. When I say use a calculator to do this problem, it's going to take you less time because you'll have practiced it, hopefully. And now I can go on and ask you a few more written questions and make sure you're really understanding the material. And that's the key. That's what I want you to walk away from this class with. So if the reason that you were asking about these topics is because you're struggling with following every detail of the calculations, relax. Okay, make sure you understand the broad concept. Please write to me with any more questions. I will be off from work today because of the storm. And let me just mention, I fully expect to be in tomorrow. I expect that our inefficient government will be able to get their act together at least and get the roads cleared by tomorrow night, now that the snow has already ended. Should that not be the case, I will be in touch with you if the university decides that they need to keep things closed, or if I'm not able to get there, I'll be in touch with you. But for right now, expect me to be in class. Keep in mind, and if you look at the university website, you'll find this rule, and obviously I would do it even if it wasn't a rule. If you don't think it's safe to come to class, and at University of Hartford, I'm assuming almost all of you are commuters, otherwise you would not be taking a 7:30 class. If you don't feel that it's safe to come to class, drop me an email and let me know. Okay? And as I said, I won't let you take the quiz later, but that quiz just won't count. So please do not put yourself into a position where you're doing something unsafe just to take my quiz. Let me know if you have any further questions. I think I've addressed everything that was sent to me. If I get any more, today is Tuesday. I said the cutoff was Monday. However, I'm around today because I'm not at work, so if I get more, I'll do my best to answer them as well. I'll see you tomorrow.